All right, well, thanks for joining me today for this training session on marine diesel engines and more specifically the additization treatment of heavy fuel oil that's used by large marine ships. My name's Eric Bjornstad. I am the Technical Information Director here at Bell Performance in Longwood, Florida. And today what we want to talk about in our time together is that we want to cover the major considerations that are entailed when you talk about marine fuel oils and their properties and the problems that they cause, and then also, of course, the solutions for those problems. So what we're going to discuss today, you can see on your screen, we're going to talk about marine fuel oils, some of their properties, their nature. We're going to talk about their pre-combustion fuel issues. We're going to talk about the problems that they are associated with during fuel combustion itself. And we're going to talk about post-combustion concerns as well. For each of these types of problems, we're going to talk about what are the causes associated with those, and then the solutions that are available to ameliorate those causes. And specifically, when we're talking about solutions, we're going to talk about, what are the characteristics, what are the things that a marine fuel oil user would need to look for when they were looking to solve one of these problems. So to get started, first of all, we will go back to the beginning by considering marine fuel oil and specifically how it's made. Marine fuel oil is created by blending secondary residual fuels with different cutter stocks. Now, as depicted by this graphic here, you can see a bunch of different kinds of things that go into creating this pool of marine fuel oil. You've got long residue, you've got straight run gas oil. These are the different parts at a refinery itself: the vis breaker, the catalytic cracker, the vacuum distillation unit, the atmospheric distillation unit. And so kinds of products that come from these places: the long residue, the short residue, vacuum gas oil, cycle oil, slurry, vis broken gas oil, things like that. And a refinery will take essentially leftovers of these, and they can blend them all together, and they can create this marine fuel oil. And the characteristics of the marine fuel oil depends on a couple of things. Depends on the characteristics, first of all, of the crude oil that's going into it. Remember that crude oil is not a homogeneous, it's not the same everywhere around the world. You can take crude oil that comes from Saudi Arabia that's considered what they call light sweet crude, and you compare that to crude oil that's coming out of the North Sea or crude oil that's coming from, let's say, Venezuela, and they can look absolutely completely different. And so they have different properties, they have different components, and so the properties and the makeup of the crude oil very much influences some of the properties of the marine fuel oil. And then, of course, another thing that influences the characteristics of the residual marine fuel oil are the kinds of refinery processes that are employed to make it. So the reason why we mention this is because marine fuel oil characteristics, they impact how the fuel behaves when it's being used, and they impact and have a definite relationship to the problems that the marine fuel oil brings with it. So when crude oil is processed at the refinery, it gets split into the different classes of products like gasoline and LPG, natural gas, and naphtha, and number one and number two diesel fuel, and those kinds of things get split into the different products that come out of it that the market uses, and by and large, these products get divided into either distillate products or residual products. Now, gasoline and diesel fuel, the number one and number two diesels, those are considered distillate fuels, whereas the heavier things, the things that are left over, essentially, when those things are taken off, things like heavy fuel oil, those kinds of things are classified as residuals. Now, historically, as you can see from the graphic, you go back to, let's say, the early 1970s, typically you would get between 52 and 65% of the crude oil would come off as distillates. Now, this says 35% residue, which means 65% distillate. And so what we mean by that, of course, is that, if you go back to the 1970s, this part here, this is where the gasoline and the diesel, number one diesel and the LPG and the number two diesel fuel, that it was about 65% of the crude oil gave us those kind of products, which means that about 35% of the crude oil was what was left over that they could get things like marine fuel oil and heavy fuel oil out of. Now, fast forward to today, and you can see that there's a stark difference here. Today, because of different processes like cracking processes that they have been able to employ, they're getting a lot more distillate fuels out of it. So today, the ratios are more like 90% distillate and only 10% residual. In fact, it can even be lower than that. I believe the most current data shows that they can get 93% distillate and leaving only 7% residual. So we're only getting maybe 7% of the crude oil volume is residual product. This, of course, includes heavy fuel oil and heavy marine fuel. And so the fact that we're getting a lot less of the residual fuel than we used to, well, this impacts the characteristics and the properties of the marine fuel oil that we pull out of this residual. Now, these are typical properties of heavy marine fuels that are in use today. You can see that all of these have specific properties that are deemed necessary enough to be adhered to that they need to be measured. So some of the ones that we can see, you can see density and viscosity. These density and kinematic viscosity, these affect the energy value of fuel, and specifically the viscosity affects how the fuel gets atomized into the combustion chamber. And you can see that the density doesn't really differ unless you're getting talking about residual marine gas oil 35. But by and large, these are about the same. The kinematic viscosity, though, is different between RME 25 and, let's see, RMG 35. Density is also important. It's important to be measured because before marine fuel oils are used, typically they're purified by using a centrifuge. They get run through a centrifuge. Centrifuge go force, strips out some of the heavy things that might cause wear inside of the engine. In order for this process to work, the fuel oil's density must be different from that of water in order to do this. So that's why they measure the density. You've got sulfur content. Sulfur content is specified or capped for environmental reasons and also to prevent corrosion. The maximum sulfur content for fuel that's used in the open ocean is actually not 5%, but it's actually 3.5%. That changed. Contrast that with when the ship gets into designated specific areas that are closer to populated areas or closer to port. Let's say, I'm not sure what the mile range, but let's say it's within 15 miles of the coastline. When the ship gets that close, they have to switch to much lower sulfur fuel, only 0.1% or about 1,000 ppm sulfur content. And that's been in place since January 2015. So sulfur is important because of environmental concerns and also because of corrosion concerns, which we will touch on a little bit later. Other things that they look at, total sediment potential and ash percent. Well, that should be pretty well self-evident what those mean. Flash point, they definitely need to make sure that flash point is adequate because flash point affects combustibility. In fact, the regulation is that the flash point of any fuel that is used in a ship's engine room must be at least 60 degrees centigrade. And so that's why you see all these minimum 60%. If it was too low, if it was lower than that, then it could almost spontaneously ignite in the warm conditions of the engine room. It would be a safety hazard, obviously. Other things, vanadium. Vanadium content affects corrosion. Aluminum and silicon content, you see these inorganics around all in here. Aluminum plus silicon content is capped because excess amounts of that relate to or can contribute to the abrasiveness of the fuel, as well as influence its ash-producing characteristics. And they also use this specification, the aluminum plus silicon value. They use it to check for remains of catalysts that might be in there after catalytic cracking. Most catalysts that are used in the refinery contain aluminum or silicon. And so if you have an elevated level of this in the fuel, well, what that can tell you is that they didn't get all of the catalyst out. And an elevated aluminum silicon level, that can cause damage to the engine. They don't want that, obviously. So it's capped off at 80 parts per million by weight. That's milligrams per kilogram, ppm by weight. So properties of the marine fuel oil will influence how it performs and can also be a determining factor in how likely that fuel is to cause problems. And so that's where we start to explore this specific issue, the likelihood that it's going to cause problems. That's what we want to look at next. Now, as we said, marine fuel oil is made from a combination of secondary refining products. They're essentially the residual leftovers from the crude oil. And because of this, marine fuel oils can tend to be prone to a number of different issues, which are usually categorized as pre-combustion issues, combustion issues, and post-combustion issues. And so this is where we want to do a rundown and a brief overview of the typical problems that are associated. We say associated with secondary refining products, but what we really mean in this context is problems that are associated with marine fuel oils. So first one, heavy sludge formation in tanks due to the precipitation of asphaltenes. Definitely a problem. The blocking of filters and centrifuges with sludge. That sludge comes from here. So these two relate to each other. Poor fuel atomization. Remember we talked about how viscosity influences that. And then hand in hand with that is poor ignition and poor combustion of the fuel. You know, if you're depending on the fuel to do certain things like burn in a large internal combustion engine and provide the ability to do work, well, poor ignition and combustion is going to it's going to be a big hamper on that, isn't it? More problems. Damage to fuel pumps due to catalytic fines. We just talked about that with a fuel that has excess inorganics or excess aluminum and silicon. The fuel pumps, the piston rings, and the liners, those are the things that can get damaged if those catalytic fines are not sufficiently removed from the fuel. Increasing frequency of changing injectors and overhauling pistons, that relates to this and some others as well. And so if you have this, well, that influences budget that's associated with the use of that fuel. High temperature deposits and erosion of exhaust valves. We're going to talk more about hot corrosion issues. Definitely a big problem, and so definitely one that's worth exploring a little further. Still more problems: fouling of turbocharger rings, fouling of rotor blades, fouling of exhaust gas economizers. Those are all areas of the combustion system that can get fouled by certain things. And the likelihood that they do get fouled depends on, in part, on the composition of the fuel. Of course, pollution of the environment due to unburned fuel emissions, that's obvious. There can be some compatibility issues if you try to mix marine fuel oil with other types of fuels in the same storage tank. That, I think, is a little bit less of an overt problem. But as you can see, we had 3 slides here that listed off all of these potential problems. So it should be pretty well evident that users of marine fuel oil have a lot to contend with. So let's look at some of the more important ones a little bit more closely. Remember, we classified them as pre-combustion, combustion, and then post-combustion problems. So let's start at the beginning. Let's go to some pre-combustion considerations like marine fuel oil stability. Now, when you're talking about stability, whether you're talking about gasoline, whether you're talking about number 2 diesel that's used for a generator, or whether you're talking about marine fuel, the same principles apply. Stability is defined as the fuel's ability to resist change in its properties or in its physical specifications when related to time and temperature. That's what stability is. Now, related to that, the issue of compatibility. Compatibility, when we talk about a marine fuel's compatibility, well, that's the ability of the marine fuel to remain stable when blending. Now, the reason we bring both of these up is because when you have a high asphaltene presence in the fuel, that can cause negative effects on both stability and compatibility. That's why we say instability and incompatibility of marine fuels are related or can be related to the asphaltene presence in the fuel. So let's look at these asphaltenes a little bit closer. Now, asphaltenes. All petroleum obviously is made up of different kinds of carbon molecules, and all petroleum, we'll say all crude oil comes out of the ground containing some amount of asphaltene molecules. Now, asphaltene molecules are these huge macromolecules that contain lots and lots and lots of carbons. They have a high carbon to hydrogen ratio. What that means is that typically, if you were to take the number of carbons and you were to take the number of hydrogens and create a fraction out of it, there's more carbons relative to hydrogens. Basically, all you really need to know is that they're large molecules that have lots and lots of carbons in them. And because they're large, because they have a high carbon content, that means two things. That means that they are heavy, they have a high molecular weight, and if you were to burn them, you would get a lot of energy out of them because you have a lot of carbon-to-carbon bonds that can be broken to create heat. Now, asphaltenes normally, in unprocessed crude oil, normally they exist as these micelles in the fuel, in the crude oil. And they exist, they're in a naturally stable state. And the reason why they are stabilized is because there are resin compounds in the crude oil and then also in the fuel that help to stabilize these and keep them essentially in homogeneous combination in the fuel. In fact, you can see that stable fuels have a high resin to asphaltene ratio. The natural resins have been preserved through processing, and if you have a lot of resins relative to asphaltenes, well, you're going to have a relatively stable fuel. However, if you take that fuel, or if you take that crude oil and you run it through some severe processing processes like visbreaking, what that can do is unfortunately, that can destroy resin content. So it will lower the resin content. And so if a high resin to asphaltene ratio, if you flip this high to low, well, then it stands to reason that you're going to lower the stability of that fuel. We used visbreaking as an example of a severe processing process. Visbreaking basically is the process of you take oil, crude oil, heating oil, whatever. You take some kind of it in a furnace and you heat it up to reduce its viscosity, and you basically heat it up and you thermally crack or break apart the large molecules. You turn them into small ones. If you've been through any of our other trainings, we have talked a number of times about cracking processes and about how those processes are what enable them to take the residual fuels and turn them into distillate fuels. Basically, to take large molecules and turn them into small molecules. And that's basically what they're doing here. So when they use visbreaking and things like that to squeeze out more gasoline and more on-road diesel, the stuff that's left behind, the marine fuel oil that's left behind, has a lower resin content and thus is less stable than marine fuel oils that did not come from crude that has undergone this process. So things like visbreaking, resins that keep the asphaltenes in homogeneous suspension, and so this resultant instability manifests itself as asphaltene dropout. Now, these here are some pictures of some asphaltene structures. As you can see, this is a chemical, a computer graphic generation. You can see all of these are carbon molecules. I believe that the white ones are hydrogens, but you can see that this is a very large molecule that has a lot of carbons in it. This is another drawing. This is each one of these points here is a carbon. You see, it may have a nitrogen mixed in here, might have an oxygen, might have a sulfur. But by and large, these are good examples of what some asphaltene molecules look like. The word asphaltenes themselves weren't discovered until 1837. There was a gentleman named, I believe his name is Boussingault. I believe he was French, would have been Flemish. And he was doing research on some oil, some bitumens, he called them, and he noticed that the distillation residue of some bitumens that he was doing some work on, he said that they had what he termed as asphalt-like properties. And so he termed this distillation residue, they termed them asphaltenes. And asphaltenes normally have some uses out in the marketplace. When you get asphaltenes in the form of asphalt or tar or bitumen products that come from oil refineries, well, those are often used as paving materials or as used in shingles or used in waterproof coatings. So that's how they get monetary value out of these extremely large residual compounds that are left over. Now, asphaltenes consist primarily of carbon, hydrogen, nitrogen, oxygen, some sulfur, as well as trace amounts of some things like vanadium or even nickel. The carbon-hydrogen ratio is approximately 1 to 1.2, so it's very low, depending on what source you're looking at. And the average molecular weight of an asphaltene molecule is 400 to 1,500 units, which is really, really large. So this is what asphaltene molecules can tend to look like. Now, let's take that and let's progress a little bit further. Now, asphaltenes, we've established, they're known to be one of the largest causes of fouling in areas like heat exchangers. Now, we already mentioned that asphaltenes naturally exist in a micelle state that are stabilized within the fuel or within the crude oil. When they undergo certain kinds of reactions, they might react with paraffins under high temperatures, and they become unstable. That state becomes broken down. Now, once the protective micelle structure has been broken, then what happens is that the polar asphaltenes, that's the asphaltene molecules that have positive or negative charges, those will tend to seek each other out, and they will start to agglomerate together. And then that enables them to travel to like metal surfaces and tube walls and things like that. And that's when they form these foulant layers that start to cause problems in these systems. So this is a micrograph of what some agglomerated asphaltenes might look like. Now, asphaltenes are a contributing factor to the formation of sludge polymers in fuel. They are basically building blocks of sludge that you might find in a storage tank. They act as polymers. We've given the definition of a polymer here that you might remember from chemistry class. A polymer is a large molecule that's made up by taking many smaller units and basically linking them together. So asphaltenes act as building blocks for heavy sludge dropout. As such, if you want to prevent this from happening, if you want to prevent asphaltenes from forming polymers and from forming large sludge molecules, what would you do? Well, you would use something like a dispersant. Now, a dispersant is a class of chemical, a class of substance that if you add it in this context, if you add it to fuel, what it's going to do is it's going to come between the asphaltene molecules, and it's going to prevent them from sticking together. It's going to essentially keep them dispersed in the fuel or in whatever medium you have, and they're not going to be able to stick together, so they're going to remain small, which means the sludge never forms. The sludge never gets large. Sludge molecules never get large enough to be heavy enough to drop out of the marine fuel oil. So, dispersants. Secondary refining processes, like we said earlier, like vis breaking, remember that, those fundamentally change the marine fuel's makeup and make it more prone to or easier to have sludge formation. So this creates a need to use dispersants and stabilizers. Essentially, dispersants and stabilizers, they take the place of those resins. Remember those, the resins that used to be naturally present to act as dispersants. Well, if those get destroyed, we have to substitute something in their place. And that's what an asphaltene dispersant and an asphaltene stabilizer will do. You'll put them in the fuel, they'll keep the molecules apart, keep them from growing larger, and keep them from becoming problematic. So if you use a dispersant in a marine fuel oil, what you get is you get less fuel sludge dropout, you get less blocking of filters, you get less presence of asphaltene in centrifuges, things like that. So asphaltene dispersants definitely are an essential thing to use in marine fuel oil if you want to prevent those kind of problems. So that's marine fuel oil stability. That's a pre-combustion fuel problem. Remember that. Other pre-combustion fuel problems. Well, this excessive sludge precipitation, we've already covered that. Filter blockage, we covered that as well. Centrifuge overload, remember that if you have a lot of sludge and asphaltene dropout, it will show up in places like centrifuges. You can get water in marine fuel oil, very easily get water. And if that water gets in there, it can form a partial or stable emulsion, which you don't necessarily want. So that can be a problem. And of course, the aforementioned presence of excess amounts of catalytic fines like aluminum and silicon that are in the fuel. Other pre-combustion problems, fuel heater fouling, fouling of the fuel injector tips is a big one because that leads to poor fuel atomization. And of course, those catalytic fines can cause abrasive wear in, remember, the fuel pumps and the fuel injectors. So those kinds of areas can be fouled by the excessive inorganic content. This is a basic schematic of a fuel transfer system in a marine fuel oil system. When you look at the issue of fuel sludge or asphaltene sludge, there are lots of areas, multiple areas of the fuel distribution and transfer system that fuel sludge can cause problems. So you start here with the storage tank. Storage tank has a heater, obviously, and then the fuel gets transferred into all of these different areas. And so we can see all sorts of different components that it can get caught in, it can build up in, it can start to affect the performance of that specific area. Here, you've got transfer pumps here. You've got settling and service tanks. Actually, the settling tank is before the service tank. Separator pumps, here's the preheater, here are those centrifuges where if you have excess sludge, then the excess sludge will come out in here and will fill these up faster than they're supposed to. Then you've got the service tank, then the fuel goes to a flow meter, which measures, the rate of flow. It goes to a mixing tank here. And then once the mixing tank, it can then go to the engine, to the fuel injectors in the engine where it gets burned and combusted. So any number of these areas here, there are lots of areas that fuel sludge can be a problem in any number of these areas. Here you can see in I believe this is a holding tank, and you can see that this holding tank is filled probably from years of buildup of tank sludge. And this tank sludge here probably has very high asphaltene content. So that's what it can tend to look like inside of a marine fuel oil storage tank. And we've mentioned excessive sludge deposits in Centrifuges. A centrifuge's job is to try and remove this kind of stuff. Well, if there's excessive amounts of this, well, then you're going to fill that centrifuge up faster. Now, one thing to consider, though, is remember that normally asphaltenes are homogeneously blended, or they're in stable, they're in stable solution with the fuel. Then that means when that fuel engine and goes into the injectors and gets burned, those large asphaltene molecules provide heating value. They provide some of the energy value, a critical part of that energy value even. But so what's going to happen if they don't stay in the fuel and if they get stripped out by the centrifuge? What do you think happens? Well, the obvious answer is that you lose heating value. You lose part of the carbon value of that fuel that normally should be combusted and should be creating heat energy. So excessive sludge volume is not just, it's not just an aesthetic problem. It's not just, it's not just an inconvenience. It matters because it affects the heating value of the fuel. And heating value of the fuel is the most important thing. It's the whole reason why a marine user is buying it, because they need to burn it to do work. So that's why something like this matters, because it means they're not going to be getting everything that they need to get out of that fuel when they purchased it in the first place. Other pre-combustion fuel issues. You can have problems with viscosity controllers and fuel heaters, problems with the fuel filters, and of course, depositing in the fuel injectors and fouling of the fuel pumps. So here you can see an example of a fuel injector problem. This is a tip of a fuel injector, and you can see, if you were trying to describe this, you would say, well, that's excessive carbonization. What they might also call this, I think I've heard them call these as flower deposits or starburst deposits, because you can see that they kind of resemble that. This kind of stuff, this kind of carbonization gets built up over time on these fuel injectors, and when it kind of stage, how likely do you think it's going to be that that fuel injector is going to be able to atomize the fuel the way that it's supposed to? Obviously, the answer is it's not very likely at all. So the result is going to be inadequate fuel atomization, and that's going to affect the adequacy of combustion of that fuel, which means that the performance of the entire system is going to be compromised by something like this. So how do you solve these pre-combustion problems? We've gone through a lot of them. This is where we have to consider, well, what do you do about them? Well, there are solutions that will address most, if not all, of these problems. The characteristics of such what we would call a best practice solution. Well, if you were a marine fuel user and you recognized that you had these problems, and you said, I'm going to look for a solution, the question is, what are the characteristics that you're going to be looking for? What are you going to be looking for? Well, you're going to be looking for these kind of things. You want something that is going to be able to stabilize and disperse asphaltenes. You want something that's going to help improve the efficiency of your centrifuging and the efficiency of your filtration. Now, this relates to this. If you can stabilize asphaltene dropout, if you can disperse it, keep it in the fuel, well, that means it's not going to come out as much in the centrifuge, and it's certainly not going to come out as much in the filters. So this will lead to this. You need something that will reduce fuel slop waste and save your fuel. Something that improves the efficiency of centrifuging by improving reduction of catalytic fines. That's probably the most difficult one, because typically the kinds of solutions that work with asphaltenes don't really affect catalytic fines. So this one is maybe one that's going to be more difficult to find, and therefore it's probably the one that we place the least importance on. And then, of course, a best practice solution should enable you to enhance your fuel atomization, improve combustion. Basically, what we mean by that is it's probably going to contain some kind of surfactant package that over time will clean the deposits out of those injector tips, which then over time will enhance the atomization of that fuel. So now that we know about pre-combustion, okay, let's move on to the second classification. Let's talk about problems that happen in the combustion zone itself. This is where things start to get, pretty interesting here. All right, let's talk about combustion basics here. The basics of combustion are illustrated on this slide here. You take fuel, some kind of hydrocarbon, you add oxygen, you add heat to get the reactions going, and what do you get? You get more heat, you get water, and you get carbon dioxide. That's basic high school level chemistry there. Carbon plus oxygen plus heat gives you heat, water vapor, and carbon dioxide. Right. So our definition of success here when we're talking about combustion is you want maximum, or what we call optimal combustion. If you have optimal combustion, you get the most heat out of it and you get the best fuel economy. That stands to reason. So the question is, how do you achieve this? How do you achieve this to the best degree possible? Now, we say best degree possible because just like it is impossible to build a perfect machine, it is not really going to be likely or possible to get absolute perfect combustion out in the field. You can get it in the laboratory because you're controlling everything that goes into it. So the goal out in the field is to try and get as high or as close to 100% optimal combustion as possible. That's the goal that we are always working towards. Now, what are the elements that go into getting as close to optimal combustion as possible? Well, we can have an acronym MATT, M-A-T-T. First thing you have to have is you have to have a proper mixture of air and fuel. You have to have proper atomization of liquid fuels into the combustion zone. And typically what happens is that A happens first and leads to M. Atomization leads to mixing of the air and the fuel. You need the proper temperature of the air of the air and the fuel, and the zone temperature must be properly maintained. There needs to be enough environmental heat to be able to satisfy this part of the equation. And then, of course, proper time must be provided to complete the combustion processes before the gases of combustion come in contact with the heating surface, because once those gases of combustion come in contact, then they will not combust as properly as they should. So if you have all these four elements, you're going to be a lot closer to having optimal combustion than if you didn't have them. So let's look at what happens during combustion, and the reason why we're going to look at this is because this is going to relate to some of the best practice solutions, especially some things that are present in things like the Bell Performance Atomics marine fuel oil treatments. So in order to understand those elements of the formulation, we need to understand what happens in combustion itself. So combustion, of course, combustion happens very, very quickly. So all the things that we're going to talk about here, we're talking about microseconds or milliseconds here. But combustion itself is a staged process. The average person thinks of it as just something that happens. Boom, you light something and boom, it explodes, or boom, it catches on fire and starts burning. But what's actually happening at that time is a multi-stage process. So the first process here, specific to heavy fuel oil, is what we call the pre-ignition process. You have a droplet of oil or a droplet of fuel. This could even be a particle of coal if you wanted, but it is a droplet or a particle of hydrocarbon that's going to be burned. So this droplet gets heated, and as it gets heated, it starts, some of its components, some of its more volatile components start to evaporate. And then eventually they reach a point where they evaporate enough that they will actually start to self-ignite, because remember, this droplet's heated, so there's a lot of residual heat that's floating around here. This could be inside of a furnace. And so this gets heated, the volatiles start to come out, and then they're going to self-ignite. They're going to catch fire. That leads us into the second. The volatiles combust. They start to combust. The volatile constituents of the oil, and of the cracked products inside of that oil. They start to burn. They create this flame envelope that surrounds the droplet here. So remember, when they burn, what are they going to be doing? They're going to be producing a lot of heat, and they're going to be breaking carbon-carbon bonds. And so this combustion of volatile stage, number 2, ends when the flame starts to die away because it's using up all of the flammable materials in this droplet or in this particle. Third one is now what you're left with. When the flame dies, then you're left with this stuff called coke. The coke is essentially the residue that's left over when all of the lighter, more volatile things have been burned out of that droplet or out of that particle. So this is a coke particle. The flame dies down, and you have hot gases, including oxygen, that start to go around the surface of this coke residue. And the coke residue actually increases in heat and burns at 1400 to 1700 Kelvin. Now, unfortunately, I don't remember what the Kelvin to centigrade or Fahrenheit conversion is, but it's pretty hot. So this stuff left over here, this stuff is called a cenosphere. At the end of stage 3, you have an unburned cenosphere of coke, residual coke that's left over. So that's the 3-stage process. You have all the volatiles came out, they burned, they produced heat, and then whatever coke was left over is going to be, whatever coke was present is going to be left over at the end. So to summarize the combustion process here, you start with a delay period between the beginning of fuel injection and the start of ignition. Now, we didn't really touch on this. All we did was we started a little later in the process. We started after the injected into the hot zone. But before that happens, when it is injected, there's an ignition delay. There's a period of time that passes between when it shows up in the combustion zone and when it starts to burn. Typically, I think what happens in this delay period is that it's it's increasing in heat all the while, but there is an ignition delay here. Once that delay passes, then you get the rapid combustion of the fuel. That creates a rise in pressure inside of inside of the cylinder. If it was in a boiler, then the pressure rise would be a little bit less. But if it's in a confined space like a cylinder, like a large large internal combustion engine, that's what I was trying to say. If it's a large internal combustion engine, you're going to get a higher, you're going to get a more noticeable rise in pressure. The fuel then continues to be injected because all of this is happening at the beginning of the injection process, because remember, it's happening really, really fast. So you get steady combustion of the remainder of the fuel as it's being injected, and then you have an after-burning period where the remaining unburned fuel from that injection stroke, it mixes with oxygen, and combustion is complete. Now, if you're, this is how the combustion process works if everything happens as it's supposed to. But we know that there are certain things that can come into play in real life that can skew or move combustion away from the optimal. And what are they? Well, if you have less than optimal atomization, let's say that you've gotten carbonization or fouling of one of the fuel injector tips, and so that fuel injector does not spray it into the combustion zone in as fine an atomized mist as it's supposed to, well, then the fuel's not going to burn to the optimal level. You can get what they call slow burning fuel. That's basically fuel that has poor combustion specifications. And then also, if the operator has to play with the excess air in order to cope with an acid production problem, that can definitely affect fuel combustion, because you need to have enough excess air. You need to have enough oxygen, because oxygen is supplied by excess air. You need to have enough oxygen in order to burn the volume of fuel. from a stoichiometric standpoint. You have to have enough oxygen to burn all the fuel that's available. But sometimes, and we will look at this a little bit closer in a few slides, but sometimes the operator has to play around and alter the excess air because they're having to prevent acid damage. And when that happens, they're going to lose efficiency on the combustion side. Other combustion problems that can rear their heads. You can get piston fouling, you can get deposits, you can get premature piston ring failure. The cylinder liner can get accelerated, so it wears out faster, and you can get fouling in places like the Scavenge airport, and under the piston. So you can have a lot of different kinds of combustion problems that can go on. In fact, this is what some of these look like. This is what the top of a piston crown that's been fouled, that's had acid damage, that's what that can look like. These things here, those are acid droplets that have condensed on the top of that piston crown. And one thing you should be able to get a sense of when you look at this is a really large piston. This is not a Ford F-150 diesel truck that we're looking into the engine. This is a large marine ship. And so this piston here, this piston top, is much larger than the average person probably is used to. In fact, you can see even better the scale of what we're talking about here, because this is it may not be the same piston, but it is another example of a piston. You can see all of this fouling. You can look at the flaking and the metal damage that's happened up here. That's not normally supposed to look like that. And when you get a piston that's fouled to this extent, this is going to be going to be really expensive. This is a problem that did not just happen instantaneously. This problem developed over a long period of time. And this is what some of the scavenge ports. The scavenge port is where the exhaust gases inside the combustion chamber, after the fuel's been burned, after the cylinder has completed its stroke and is on its way down, typically the exhaust gas, the spent gas, will then be forced out of the chamber so that new air can come in, so that new fuel can be injected. So it leaves via the scavenge port. Well, if that has, let's say, excessive sulfur or other kinds of constituents in it, which again came from the fuel, if you remember, if it's problematic in its makeup, essentially, well, then over time you can get these kind of scavenge port deposits. So what are the options for addressing these kind of combustion problems? What are the characteristics of the ideal best practice solution? Well, a best practice solution for solving these combustion problems, it should be able to do these three things. It should be able to promote an earlier completion of combustion of the fuel. And what that gives you is a longer burnout time, and it gives you less soot production. Soot being unburned carbon, so it lowers your unburned carbon and essentially moves you more closely to the goal of complete combustion. It should enhance oxygen transport during coke combustion. That enables you to burn more of those unburned carbon centispheres that we saw earlier. And it should clean fuel injectors, pistons, keep them free from carbon deposits. So generally speaking, when you're talking about what kinds of things are available to do these kinds of things, when you're considering that, now you're moving into the realm of metallic combustion catalysts, the kind of metallic catalysts that are present in the ATX marine fuel oil treatments. Now, unburned carbon, or partially burned carbon, the presence of that after combustion is a sure sign that the combustion process has not been completed to the optimal level that the engine was designed to. So if you've got soot that's coming out in the emissions, or if you're seeing carbonization of certain areas in the combustion or the post-combustion zone, well, what that tells you automatically is that carbon should have been burned. That should not be there. And that means that you're not getting full combustion and something is causing that. Now, what could cause that? Well, it could be the fact that there wasn't enough oxygen. It could be that the fuel wasn't, atomized optimally, because droplet size definitely can impact, how well something combusts in a given environment. But, whatever it is, it means, bottom line, you're not getting everything out of the fuel that you're paying for. And so, in order to address this, organometallic combustion catalysts have been shown to be able to make substantial inroads in solving this kind of problem. You might also hear them referred to as surface catalysts or radical generators. We'll talk about that a little bit. We'll explain that here in a minute. But basically, in order to understand this whole thing of organometallic combustion catalysts, you have to go back to the 1950s. There were scientists, I want to say that they were at DuPont. Sometimes I get DuPont or Dow mixed up, but we'll say DuPont. There were scientists at DuPont, and they were doing research on the effect of different kinds of metals and how well they catalyzed or how well they improved combustion. And what they found was really some breakthrough work, some breakthrough results that basically told us that there were certain kinds of metals like iron or cobalt, even ones like cerium and barium and things like that. And not only did they find that some of them, markedly improved combustion completion by, pretty large percentages, they found that if you use combinations of them, they had synergistic effects that were greater than the sum of the individual components. So the work on organometallics really was really revolutionary in the 1950s and showed pretty conclusively that certain combinations of organometallic metals, if you put them in the combustion zone, in the hot zone, in the presence of the fuel that's being burned, you can basically maximize the combustion of that fuel. And so how do these work? Well, we called them a surface catalyst. And basically what you've got is, remember that when you break it down to the micro level, the fuel oil is a droplet. Remember that droplet shape when we were talking about the stages of combustion. Well, the fuel oil is a tiny little droplet. And you remember that as it heated up, the volatiles came out and then those burned and it created a flame sheath around it, et cetera, et cetera. What surface catalysts do, what organometallic combustion catalysts do, is they do two things. First thing they do is that as they interact with the hydrocarbons, they increase the number of radicals of hydroxyl and oxygen that are produced. Now, a radical, that's a chemistry term. A radical basically means half of a molecule. It's an unfinished molecule. Like, for example, you know that water is H2O. It's hydrogen bonded to an OH. If you were to split that bond and take away the hydrogen, what you would be left with on the other side is an OH radical. It's like half of a water molecule. Now, an OH radical is incomplete, and it's immediately going to run around and look for another molecule to react with so it can make itself whole. Now, the reason why this matters is because if you can increase the amount of OH radicals that are formed, these tend to be really, really reactive. And as such, when you put them in a combustion scenario, they actually increase and help drive complete combustion. They improve the completeness of combustion, basically. So one of the things that organometallic combustion catalyst does is it increases the amount of these, and it increases the amount of volatiles that are formed around the fuel oil droplet. The second thing that it does is lowers the activation energies. Now, all you really need to know about this, and this is just surface level chemistry. We don't need to go any further than that, because if you talk to a customer, or if you are a customer yourself, you're not necessarily going to care about the absolute intricacies of this. So this is just basically give you enough information to be dangerous kind of thing. Second thing that organometallic combustion catalysts do, they lower the activation energies for the combustion reactions. Now, if you remember, Combustion is a chain reaction series of chemical reactions where carbon-to-carbon bonds are being broken and heat's being produced. In order for those to happen, every chemical reaction needs a certain energy input in order to make it happen. It's what it's termed as the activation energy. What the combustion catalyst does is it lowers the amount of energy needed for a specific link in the chain to happen. And so what you get is that you get more combustion reactions happening earlier and at lower temperatures. Basically, it comes down, it results in faster combustion and more complete combustion. Now, one clarification that we want to make on this, because this can be a little bit of a misunderstanding. Okay, when you get this, when you get lower ignition temperatures, you get faster reactions, more reactions happening. What you're going to get is you're going to get a greater amount of heat that's being produced earlier in the combustion process. Now, however, there's a difference between saying that and saying that you're going to increase the maximum amount of heat that you can get out of a given unit of fuel oil. Now, what we mean by that is, let's say that let's just say you have a gallon of fuel oil, and a gallon of fuel oil, we'll say, if you burn it to completion in a laboratory setting, if you figure out what its heat of combustion is, the maximum amount of heat that is produced when all of that fuel oil, all of that hydrocarbon is completely combusted. Every hydrocarbon, well, in fact, everything has a heat of combustion. That's one of its properties. And let's say that if you completely combust a gallon of fuel oil, you will get 148,000 BTUs of heat out of that. Now, that being a fundamental property of that heavy fuel oil, you can never get more than 148,000. But on the flip side, if you were to put that in a typical engine, you're probably not going to get 148,000. You might get 140, or you might get 142. And so the difference between the 140 that you get in real life and the 148, that's the maximum, that's what we're trying to bridge by the use of these catalysts. What we're not saying is that a combustion catalyst will cause the maximum amount of heat, that 148,000. We're not saying that it's going to magically kind of like if you have a 55-gallon drum, you can't do something fundamentally to that to make it into a 60-gallon drum without like tearing it apart or something. So that's just an important distinction we want to make sure that's understood. Combustion catalysts, like the ones used in whether it's ATX 1004 DSC or 1005 SSD, or one of the catalysts used in one of our power generation formulas, those bridge the gap between that 140 and that 148. They do not change the fuel oil and change the maximum amount of heat that you can get, because that's a fixed property of that, and that would definitely not be something we would want to go around claiming. So the ATX streams from Bell Performance, they deliver combinations of combustion catalysts that aim to solve these marine fuel combustion problems. So if you take fuel that was burned without a combustion catalyst, remember we talked about the cenospheres. This is what a cenosphere looks like. This is a carbon particle. Well, this has got lots of carbons in it, but this is basically, this is what we could call it a soot particle if you wanted. You can see it's got little holes in it, but by and large, it kind of looks like this. But when you take a combustion catalyst and you run it through the same process, you get something like this. Notice the difference. First of all, there's less of this than there is of this. You can also see that it actually is kind of hollowed out, isn't it? And that's because more of the carbon inside of it got burned completely and disappeared as carbon dioxide. Basically, this fuel gave more heat than this fuel did, and it was all because an organometallic combustion catalyst in ATX was used to treat that fuel. Now, Other evidence that of the difference between with and without catalysts. Here you can see some differences in unburned carbon levels that are graphed between untreated fuel and then the use of specific kinds of metallic combustion catalysts. So the first one, untreated heavy fuel oil, kind of fuel oil was used for all these because you know, as in order to be scientifically rigorous and meaningful, you do have to do something like that. So untreated fuel oil, they burned it. They were left with about, well, they burned it under controlled conditions. They were left with, we'll say, you know, 1.3, 1.35% by mass unburned carbon. Yeah, that's okay. They took the same fuel, same conditions, added an iron combustion catalyst. Boom, 60% reduction in the unburned carbon that's left. Same for calcium, 62% reduction. When they took iron and they mixed it with a dispersant and then burned it, they got a little bit more. They got 66%. When they added ATX 1005 SSD, that has, I believe, 3 different metallic combustion catalysts. They got an 88% reduction in unburned carbon. An 88% reduction means that for all of this carbon that would normally have been left over, now this has turned into heat and it's turned into work for that ship, which means that that user who used ATX 1005 is getting a lot more out of their fuel that they paid for. So the use of combustion catalysts in marine shipping fuels definitely gives positive benefits for the customer, including most obvious one, better fuel efficiency because you're getting more complete combustion. Third type of problems, post-combustion problems. This is where we're going to start talking about things like corrosion issues. All right, now, so I know we've been going at this for a while, so we're going to try and you know, talk as completely as we can about post-combustion problems without extending this too much longer. So just bear with me and we'll get through this. So we've already looked at pre-combustion. We've looked at also at combustion. Now, what about those post-combustion issues? It is, like I said, this is where we're going to consider these corrosion issues. Now, corrosion, whether it's hot corrosion or cold corrosion, it's a big problem for marine fuel users. Really, not just for marine, really for anybody that uses heavy fuel oil. You know, power generation, industrial, things like that. You know, corrosion problems are a universal problem for anybody who uses that type of fuel because it does stuff like this. You get corrosion in areas of the engine that are closest to combustion, which means this is the top of the piston crown. Piston crown obviously is really close to combustion, and over time, you got this corrosive damage that happened on the top of this piston crown, and this piston is going to have to be replaced at, you know, pretty substantial expense for the shipping company. And this was entirely fuel related. You know, we saw a similar picture to this earlier. This is the same type of piston crown deposit. Do you remember we saw the acid deposition? Well, this is another example of it. This is going to have to be replaced at you know, relatively high cost to that company. So, and this is all fuel related. Well, how can we say, you know, why is high temperature corrosion fuel related? You know, more deposits. These are damaged valves. These were corroded over time. This is a nozzle ring that was corroded by vanadium deposits that came from the fuel. So let's examine why this is, why high temperature corrosion, we can say it is fuel related. Okay. Fuel oil coming from petroleum, you know, the makeup of that fuel oil is a primary causal contributor to the high temperature corrosion problems. Specifically, when we talk about the fuel composition, we're talking about the inorganic makeup, the amount of the different kinds of metals that fuel oil contains. So all fuel oil, because it comes from crude, it contains inorganics like sodium, calcium, iron, sulfur, and most importantly, vanadium. In fact, vanadium and sodium sodium, and sulfur are probably the three most important ones for this discussion. Now, when that fuel gets burned, when it undergoes combustion, those inorganics, they get oxidized. They combine with oxygen from the air, and they form oxide complexes of all different kinds, similar to ones that we see here. Now, depending on what the makeup of the complex is, depending on whether, what kind of metals in it, what combination of things, well, they have different physical properties, including different melting points. You can see here that some of these, like pentasodium vanadyl vanadate, which is 5 sodium, 2 vanadium, 4 oxygens, combined with another 11 molecules of vanadium. This is a pretty large complex combination of inorganic oxides here. It has a melting point of 535 degrees centigrade. If you go to a simpler one like sodium orthovanadate, it has a melting point that's 300 degrees higher. Now, the reason why this matters is because when you're talking about a hot zone, when you're talking about a high temperature area, one of these is more likely to be liquid in that area. And I think you can guess that it's going to be this one, or these two only have melting points that are in this low 600s. So some of these are going to exist perpetually in liquid form, the ones with the lowest melting points. And the melting points matter because the melting points of these influence their physical characteristics, and they influence how corrosive the deposits are. Now, this is a relatively complicated graph, but what it shows us is it's designed to show us how the melting points of different complexes can be, first of all, dependent on the ratios of sodium and vanadium that they contain. And in other words, the sodium vanadium that comes from the fuel oil, right? Now, it doesn't come from the air, it doesn't come from anything else. The sodium content and the vanadium content of the fuel oil directly influences all of this. So that's the first thing it shows. And so what we can see is, you can see that as the ratio of vanadium to sodium changes, then what you can see that the melting points of the complexes tend to change. So you start here, sodium oxide, there's no vanadium in it. It's got a 1275, right? When you start adding some vanadium to it, it actually goes down, bottoms out around 700. Then as you go up to here, this one actually has a high, but this typically here, when you get 2Na2O V2O5, and you get this kind of sodium vanadium complex formed, and this kind. This area in here is where you get the really lowest melting point deposits, and you get the highest amount of slagging corrosion that happens. And then as you increase it, you get more superheater corrosion out here. Now, that's all you really need to know about this. The big takeaway with this is both low sulfur fuel oils and high sulfur fuel oils, they all produce these kind of corrosive deposits that have low melting points and directly contribute to these kind of corrosive issues. So the composition of the fuel oil directly contributes to corrosion damage in these systems. So how do these corrosive deposits form? Well, it's rather a simple sequence, really. The first thing is that you get things like V2O5, which is, I believe, is called, well, I want to call it a vanadate. A vanadate is actually a bunch of different things, but V2O5 is formed and sodium oxide is formed during the combustion sequence. Then they combine with ash particles and they act as a binding agent, and they make the ash particles stick to the metal surfaces. Once that happens, they undergo some corrosive reactions. The V2O5 and the sodium oxides react on the metal surfaces, and then they start to flux with iron called magnetite, and this is where the corrosion happens. The liquid here fluxes with this, and it exposes the underlying metal to very rapid oxidation with the oxygen in the air and corrosive damage. This is a big problem for heavy fuel oil users. They do not want this kind of stuff to happen. So how do they keep it from happening? What are the best practices to combat this problem? Well, the traditional solution has been to add some magnesium into the equation, because magnesium is really good at combating corrosion problems. One thing that magnesium does is it acts as an ash modifier. Basically what it does is it mixes itself in with these vanidates, and so instead of having a simple, combination of vanadium and sodium and oxygen, what you have is you have a combination of vanadium and sodium and magnesium. And what that does is it really raises the melting points of these deposits. If you have a higher melting point deposit, then first of all, it's not going to be liquid in that combustion system, and it's also, when it cools down, it's not going to cool down and form this really glassy, tenacious, hard to remove deposit. It's going to form essentially a powder off on its own. And if it can drop off on its own, then that vanadium deposit is not going to be around to catalyze the formation of sulfur trioxide and sulfuric acid like it would if it was still on the metal surface. So magnesium acts as an ash modifier, and it also acts as an acid neutralizer. It neutralizes SO3, which causes the formation of magnesium sulfate, instead of allowing that SO3 to further combine with water vapor. This should say H2O, not O2, to form sulfuric acid. So magnesium does two really important things that are highly beneficial towards solving this problem. And the amount of magnesium used, it's been around for a really long time, and it's pretty straightforward and well known how much magnesium you need to use in order to get the job done. I mean, basically, if you have this V2O5 and you add some magnesium to it, this has a melting point of 675 degrees centigrade. This has a melting point of 2800. You combine them, you get a melting point of almost 1200. This is going to be much less of a problem than this is. So that's high temperature corrosion. Now, what about low temperature corrosion? Low temperature corrosion is also a substantial problem. Now, where does low temperature corrosion occur? How does it occur? Well, the first thing you have to look at, remember we talked about SO3. Sulfur comes from the fuel oil, and when the fuel oil is being burned, that sulfur combines with oxygen from the air and typically will form sulfur dioxide, this SO2. But a certain percentage of it will then combine with more oxygen, and you'll get a certain amount of SO3 that is normally produced. Now, so this is hanging out in the in the gas. That gas stream leaves. Now, when that gas stream leaves, it's got SO3 in it, and as that gas stream leaves and it travels towards down the exhaust system, it's going to start cooling down. As it cools down, this SO3 is going to combine with water vapor that's present, and you're going to get sulfuric acid that's formed. Then, once that exhaust stream, now normally this is a vapor. Okay, this is dissolved in the gas stream. This is still a gas, and right now it's not necessarily a problem. But the problem happens. This exhaust stream, it's moving away from the hot zone, so it's cooling down and cooling down and cooling down. When it reaches a point where it cools down below a specific dew point temperature, then it turns from gas to liquid, and it condenses on the metal surfaces, and that's when you get what they call cold end corrosion. So the operator does not want that to happen. The operator thus has a problem. He's got multiple problems, really. He or she's got multiple problems. They want to maximize their efficiency, right? They want to get as close to maximum efficiency as possible, but they also know that they're probably going to have to sacrifice some of that efficiency in order to solve both hot temperature and cold temperature corrosion and keep those from happening, because they want efficiency, but they do not want corrosion. So what are their options? What can they do? Well, they do have some options, but most of these options come with drawbacks. When they're talking about operational options here, one thing that they can do is they can try and keep excess oxygen as low as possible. If you have, and when we say excess oxygen in this context, what that means is the volume of air that they're supplying the combustion process, because that's where the oxygen comes from air. So if they can lower the excess oxygen, then there's less oxygen available for that sulfur to combine and form SO2, right? Great. However, you need a certain amount of oxygen in order to drive the combustion process. So you can't drop it too low, or else you're going to start sacrificing combustion efficiency, and you definitely don't want that. The second thing that they can do is they can try and raise the exhaust gas temperature so that it gets further away, further down the cold end before it cools down enough to drop below the dew point. Now, how do they do that? How do they affect this temperature? Well, they do it basically by increasing the gas volume. So, which is the exact opposite of this. If they find that they're having a cold temperature corrosion problem, then what they will do is they will increase the amount of oxygen, the volume of air that's supplied to the combustion chamber. And so then what happens is you have a greater volume of air leaving that, which means you're going to have it's essentially going to cool down slower. And so you're going to have a much greater chance of staying above that acid dew point temperature. The downside to this, though, is you're going to lose more heat. So you're going to cut into your efficiency that way. So with either one of these, you have, darned if you do, darned if you don't scenario. Neither one of them is a perfectly clean solution, but the operator has to do something, right? They can't just do nothing. Areas that you can have problems with this hot corrosion. These are all areas of the system that if you run, or if you're familiar with one of these engines, you'll know exactly what I'm talking about. Exhaust valve. We've already seen examples of piston crown corrosion. We've also seen nozzle ring and turbocharger blade corrosion. How much do you think corrosion problems cost a marine ship with one of those large engines? We can't say exactly how much, but it's going to be a pretty sizable chunk. And then cold corrosion tends to happen on cylinder liner walls, exhaust valves. It can happen also on piston crowns, and then areas of the exhaust system like exhaust valve casings, trunking, gas economizers, funnel casings. So hot and cold corrosion will both target specific areas of that engine system. This is a turbocharger that has been corroded over time. You can see corrosion damage all around in this area, and eventually, replacing a turbocharger is probably the exact opposite definition of cheap. This is a pretty extreme example of cold corrosion and deposit blockage that happened on an economizer. Now, an economizer is an area that basically facilitates heat exchange. This economizer, think about a radiator, or in fact, you can see these things here. What this should remind you of, if you are at all mechanically inclined, is this should remind you either of a radiator in your car, or the heat exchange system that's on the back of your refrigerator. That's basically what an economizer is. It facilitates exchange of heat between air on the outside and liquid on the inside. And as you can see, this one got really seriously corroded on both of them and plugged with stuff that's really not supposed to be there. They're going to have to replace this. So the solution to this is to use the magnesium treatments we talked about before. If you add magnesium, remember, it's going to increase the melting points of the otherwise sticky deposits, which is going to fundamentally change their properties. But on the low temperature side, what it does is it helps minimize the formation of desulfuric acid. Remember, we said that it neutralized corrosion. It combined with SO3 to form magnesium sulfate, which is innocuous and non-corrosive, and you want this, you do not want that. So magnesium treatments that are in the ATX multifunctions, that's what MFA stands for, not only do those deliver organometallic combustion catalysts, they also deliver magnesium deposit modifiers that fix hot corrosion and cold corrosion deposits. So some of the operational benefits that someone who uses ATX would see is first of all, they'd see a reduction in the buildup of deposits of ash and carbon on all areas of the system that those may tend to build up on. They would see reduced unburned carbon because of the combustion catalyst. They'd see cleaner economizers as well. So to address all of these problems that we talked about, we talked about sludge and asphaltene dropouts. We talked about combustion, lack of optimal combustion in HFO combustion systems. We talked about hot corrosion, talked about cold corrosion. For all of these problems, we developed this ATX family of multifunction fuel treatments, and they're all designed to give these kind of benefits. They want to reduce the formation of unburned carbon deposits. They want to reduce engine wear associated with those. They want to clean economizers and keep them from getting to the condition that you saw earlier. They want to attack and reduce both low temperature corrosion and high temperature corrosion. They want to stabilize the fuel and reduce the formation of sludge dropout. And they want to produce measurable improvements in post-combustion emissions. And of course, on the storage side, disperse and eliminate water and moisture that can be inherent when you're storing, marine fuel oil. Typically, ATX is used at a recommended dosage to start with between 1 to 3,000 or 1 to 4,000. Now, you have to pick a starting point somewhere, but really, this recommended dosage does depend to a certain extent on the vanadium and sodium content of the fuels. If you have a higher vanadium fuel that, let's say, is higher than 250 ppm, well, then you would probably start with a higher recommended dosage because you want to be sure to get enough magnesium in there to satisfactorily address the vanadium and the sodium that's in that fuel. Typically, ATX is dosed into the settling tank. Either that or it's done by direct injection into the fuel line. Now, the optimal place to apply ATX is in the settling tank because then it's present in there and it's able to pick up sludge and anything that's in that tank. But we've had other users who will use a metering system to inject it basically directly into the fuel line as the fuel moves towards the combustion chamber. And this is where they get, the output of their injection system is determined by the fuel transfer pump capacity. Basically, what that's saying is that the reading system is integrated so that it's able to vary the injection of the ATX relative to how much fuel is being used at any amount of time. So, all basic stuff. There's nothing too complicated. So, ATX is the heavy fuel oil treatment line that has been manufactured by Bell Performance since 1952. Now, Bell Performance itself, we are headquartered in Central Florida, Longwood, Florida, which is just north of Orlando. We've actually been in Central Florida since, I believe, 1936. But we're even older than that. We actually invented the world's first fuel additive in 1909. Robert Bell, who is the namesake founder of Bell Performance, invented in a detergent package in 1909. He then developed one of the first surfactant packages that was able to make water and petroleum combine. He did that in 1927. Then in 1952, he developed his first heavy fuel oil treatment. We've been treating heavy fuel oil for a variety of customers and a variety of markets ever since that time. Bell Performance has national sales and distribution. We sell all across the country. We sell in Canada, Latin America, and we export both consumer and industrial fuel treatments to, I believe, more than 17 different countries, including EU, Far East, Japan and China, Australia, New Zealand, India. So Bell Performance has both national and international reach. Now, when you're looking at the types of active ingredients that are in atomics, who are the people that are most likely to use these kind of things? You might say, I'm in this kind of, the question is, why would I be interested in considering this ATX? Well, the kinds of people who use ATX to treat their heavy fuel oil, they're large users and they're small users, but they all seek the same kinds of solutions as you probably do. They want to save money. They want to reduce their fuel usage while maintaining the same or more output. So, and this is the one that everybody wants. Everybody wants to save money and reduce fuel usage. They also, however, it's just as important to them that they prevent damage to their expensive equipment and thereby protecting their capital investment. So this can be just as important as this. And then for some of them, it may be something as simple as recovering the lost fuel value through sludge dispersal. All of those kinds of things are things that ATX will directly impact and will directly provide a pretty sizable return on investment for these users. Now, some examples of people as we start to wind this down, this up to this point, this has been a theoretical discussion, but now we're talking about specifics here. Who are specific kinds of people who have been actually using ATX? Since it's been around for 50, close to 60 plus years, a lot of people have used it. But we wanted to give you a few examples here. Northport Power Station, a 4-unit system that is the largest oil-fired electric generation power station on the east coast of the United States, provides at least 25% of the power for the entire borough of Long Island. They've been using it since 2001. Primarily, their goal has been to reduce deposits for deposit control inside the boilers. And so as you can see, pictures taken, heat transfer tubes are clean, looking good. They've been a satisfied user for, this is 2016, so going on 15 years now. Over in the EU, Ireland, Tarbert Generating Station, they used it to help with their soot blowing, help remediate corrosion on their boiler tubes, and increase their boiler availability. And what we mean by that is that if you can keep deposits from building up on those tubes, then you will not have to shut down as often. So your boiler availability will be enhanced. They, at one time, were saving almost $1 million per year, $946,000 by using the ATX formula. There are other different industrial customers, both domestic and foreign, like in Ireland, Southern Milling, C&Z Soft Drink, Purcell Wilson, all of whom would save between the high 3s and the low 5% in fuel savings, which is substantial fuel savings. MC Terminal in Japan used it to reduce acid smut emissions to the community by between 19 and 50%. Also, industrial customers in Taiwan. There are a lot of industrial customers that engage in things like dyeing plastics, making textiles, manufacturing ceramics and cement. They will use ATX. They will see fuel savings reductions between 5 and 9%, along with emissions in reductions in things like SOx and NOx by 10 to 50% relative to the output unit. So those are substantial benefits that these people have been using. Now, but these are all of on-land customers. Is there any difference between what the value propositions for them and the value propositions for marine fuel oil users? Well, in one sense, not really. I mean, marine fuel oil users, they want fuel savings. If you can even if you can reduce fuel usage by as little as 1%, that's a substantial financial gain, given that these large ships use so much fuel. They also need to make sure that they control corrosion and deposits. And so if you can do that, which ATX does in the marine environment, you get substantial savings there. And of course, recapturing lost fuel value through sludge removal. The value is there both for the marine and the on-land user as well. So all of these things that we talked about, these are all problems that ATX, the multifunction treatment from Bell Performance, is all things that ATX does. And so that's why, for all of these reasons, this is why we're pretty confident in saying that, if you need a problem-solving magnesium fuel treatment or an HFO multifunctional that improves combustion and solves corrosion problems, if you need any of that, then Bell Performance ATX, we believe, is going to be the right choice for you. And so that brings us to the end of our training session on marine fuel oil treatment and the treatment of heavy marine and the Bell Performance ATX treatment. So you may have questions. If you're viewing this live, then this would be the point at which we would start taking questions. But if you are viewing this by video, then obviously there's no way for you to do that. So the best thing for you to do, we encourage you, if you have any questions, if you have any comments, then please email me. This is my personal email address at Bell Performance. I'm ebjornstad@bellperformance.net. So just send me an email and mention that you were viewing the marine fuel oil treatment training and that you had a question. I will be more than happy to address any questions that you have. So in the meantime, that concludes our training session for today. So thank you very much for joining me. Once again, I am Eric Bjornstad with Bell Performance. And thank you for joining me, and we'll see you next time.